All right, so hopefully today we're going to get into the start of what becomes, at least what I've always found to be the most fascinating part of any of this. So we'll get going, but real quick, from the stuff we've learned so far, just as a reminder, light acts as a wave, even though it has no medium that we can detect for it to pass through. We had our two postulates, and that was that the speed of light was always the same for all inertial observers, and that the rules of physics were the same for all inertial observers. We talked about those Lorentz transformations versus those Galilean ones where we made all the changes and stuff like that, and we started getting things like time dilation out of them. We talked about a light clock, which was basically just bouncing a beam of light back and forth between mirrors and then counting how often it went there and back. The time dilation we did on the train, where the person on the train saw one amount of time and the person watching from the side saw a different amount. We talked about the twin paradox, and we eventually answered the paradox part of it and figured out what would really happen. Same thing with length contraction. We talked about that ladder fitting in the barn that was too big for, but we eventually figured out what would have happened in there. And then the length and time, which it was, where for one observer it may look like time dilation, and for the other they see the exact same bit, but for them it's length contraction, and that's why they get two different results. Then we talked about correlation, how we couldn't agree on the order of events. And then we talked about adding velocities and how we couldn't agree on what velocity things were going. But then we went on and figured out how to add the velocities, and how that no matter what we did, no matter how we added velocities, we always ended up with something that was less than the speed of light. We talked about the space-time interval. It was our one thing that we could all agree on. If we all measured that out and calculated it all out, we would always agree on it, and it was a tensor. And that was how we used that to tell whether or not we could have events that were causally linked potentially or not. We did the Minkowski diagrams. Those were those space-time diagrams, which are going to become very important, especially next lecture where you use them to look at black holes. We talked about world lines and light cones and the twin paradox on these diagrams. And then that brings us to today. And so today, what we're going to do is we're going to finish up talking about energy, relativistic energy, and then we're going to move straight into general relativity after that. So most people are very familiar with Einstein's big time equation that everybody always knows, and it's just that E equals mc squared. This is the one that's very well known. All right, mc squared. Okay? And this is the one that goes around that most people always know, and you see it everywhere, but it's not quite the whole equation, all right? In fact, really, what it's supposed to be, if y'all remember this term gamma, is actually E equals gamma mc squared, okay? Gamma was that, if we remember, it's gamma is 1 over the square root of 1 minus your speed squared over the speed of light squared. And it was that factor that we used that told us how much time dilated, how much light or length contracted and all that kind of stuff. Well, it actually does go there as well. And so what this is telling us is that as we go faster and faster, we actually become more energetic. And a lot of people will make the statement, and I'm not sure how correct I think it is as far as this goes, but they say that you gain mass as you move faster and faster. And that is kind of one way you can think about it. I'm not sure it's the best way you can think about it, but there is that idea. And then we can even get the kinetic energy out of this by simply taking the difference of these two. We can do gamma mc squared minus mc squared. Because if you look at gamma and we put a velocity of 0 in there, right, then we're actually going to lose any of that velocity type term to it, and then all we have is that rest mass that's there at the top, and that's the amount of energy you have in something that's just sitting still, just based purely on its mass. The second one is its mass and its energy due to movement, its kinetic energy. And then this last one, if we take the difference between those two, we get our kinetic energy. You can take that total energy there, that's that second one, and you can do a whole bunch of algebraic manipulation to it, that I'm not going to do right now, and you can end up coming up with, oh, oops, sorry, that's supposed to be a plus sign, and you can get this version of it, which is another very useful version of it, because you can do this for particles and objects that don't have mass, because we get this term that's separate and independent of the mass. So you could put something in like a photon right here that has no mass, and it still is going to tell you how much energy it has. All right? So while this equation tells us that energy and mass are related, it kind of tells us we have to have energy to have mass, but we don't really have to have mass to have energy. Okay? And then here in physics, we stop referring to it as mass and energy, and it just gets referred to as mass energy. All right, it's just one thing, kind of like how we had space and time, and now it's just space-time. We had mass and energy, now we just call it mass energy. You can turn mass into energy and energy into mass and back and forth all you want to some limits. And this is what gets you like nuclear power and heat that comes off of things during that sort of stuff. So let's take a little look at this real quick, okay? And we're going to do a little example. And we're going to start with two balls of clay. And we're going to say each one has the same mass m. And we're going to send them towards each other at the same speed, v. And then these two balls of clay, they're going to hit together and they're going to stick. Right? They're going to stick together in the middle. Right? Some clump of clay here. Especially those of you who have taken my physics last semester, who can tell me, once they clump together, how fast are they going to be going? I got one answer. Anybody else? Thank you, Liz. Don't speak too loudly. We don't want anybody to hear you. Yeah, they're going to be going 0. If they're going the same speed in opposite directions and they collide, they're just going to stop each other. Okay? So they'll stop each other in the end, and there'll be some total mass, we'll just call it capital M, between the two of them. Can anybody tell me what they would expect that total mass, that capital M, to be compared to the original little masses?
2 times lowercase m?
Yeah. You would expect, all right, you expect capital M to equal 2 times the little mass, right? It's just each one of their masses added together. But let's take a look at this relativistically and see if that's actually what happens. So let's look at the energy, right, before they collide, okay? Before they collide, we have, if we look at them, we have 2 balls of clay. They're both going the same speed. And so if we want to know what their total energy is, it's going to be gamma mc squared. That's the energy of each individual one. There are 2 of them, so we will multiply it by 2. And then what we're going to do is we're going to give them a speed. And let's give them a really high speed. Let's say 4/5 the speed of light. 4/5 c. Okay? And then we can come in here and we can go ahead and start plugging this in. We'll get 2 times 1 over the square root of 1 minus v squared. So this is our gamma factor. It's the velocity squared, right? Over c squared. So in this case, that's going to be 4/5 squared c squared over c squared. What's going to happen to the c squareds? Yep, cancel. They'll be gone. And then times mc squared. And so what we end up with here is 2 over, and then we're going to have the square root of 1 minus 16/25, and then times mc squared, and then that's going to give us that 1 minus 16/25 gives us 9/25, and the square root of 9/25 is, I thought you were about to tell me I was doing this wrong.
No, you're
I
good.
made that one wrong. Square root of 9/25 is 3/5, and then the reciprocal of 3/5 is 5/3. And so we end up with 10/3 mc squared. Okay? And so that tells us the amount of energy that we have before the collision. So let's look at the amount of energy we have after the collision. After the collision, we have no kinetic energy at all anymore, right? All we have is the rest energy. So what we can do is just calculate this. This is capital M c squared, and that's our total energy then at that point. Okay? So the energy before, we can make these little equal signs, is that, and the energy after is that. And so, again, for physics students, what do we know about, what do we do with total energies in systems like this? It's a C word. Yeah, we conserve it, right? We conserve that total energy. That means we can say that the energy before should be equal to the energy after. We have no friction or anything like that going on, right? Which tells us that 10/3 mc squared should equal capital M c squared. The c squareds can cancel, and we're left with capital M is equal to 10/3 of little m. So we're actually going to gain some mass here. All right, this is the same kind of idea here, which goes along with, in a little more complicated fashion, with fission and fusion. All right, when you slam nuclei together into larger molecules, you end up with an imbalance of energy, and therefore you can get energy out of it. Or if you rip them apart, you can get it to release energy, depending upon what elements you're actually doing. It goes one way or the other, but you don't get a balance. It doesn't balance out for the total mass. So we end up with this extra energy here that either turns into mass, or we figure out some way to harvest it, doing this in reverse in some sort of way, and actually just get energy out of it. Like crickets in here. Okay? Maybe then I'll just skip this page since we're not liking this energy stuff. But maybe just real quick here. Relativistic units, what we can do is we can actually start to, and I won't write them all out now, but you can actually start measuring mass as a unit of energy. And when you do that, momentum even becomes a unit of energy based thing. It's like unit of energy per speed of light. And so a lot of the units actually really simplify down, and that whole dimension of mass that we talk about quite often, have to worry about, actually just kind of goes away. It just becomes that mass energy. So we don't have to worry about kilograms or anything like that anymore when you're doing this. And it does make the units a lot simpler if you do really get into that. Okay, so that was the end of that, as far as that one went. Now let's start general relativity. So special relativity is what we have done so far, and this was all dealing with inertial observers. That meant there was no acceleration and no gravity around them. Okay, everything was nice and flat, it was easy. Everybody that was moving just kept moving however they were moving, and if they did change their motions, then it was like an instantaneous change in motion. We didn't talk at all about acceleration. And there's a reason for that, and it's that it's really, really, really hard. In fact, it was another 10 years after he published this special relativity that he took to work out this general relativity. And even then when he published it, I don't believe he was even quite really ready to publish it. He just felt pressured to. So 10 years of trying to make the addition of simply adding gravity into this idea, and it gets so much more complicated, okay? So that's what we're gonna do. We're gonna include accelerations. All right? So we're gonna talk about the equivalence principle. And we're gonna start by going back to a train. Not that same train, this one's a little different, but back to a train. And in this train, we're gonna be inside this train, and it's gonna be nice and soundproofed, and it's gonna be on a nice, perfectly smooth, frictionless track, so no bumping or anything if it's riding along. And there's no windows, you can't see out of it. Okay? Is there anything that you could do to tell if you were moving? Any ideas?
You were saying jump, but that would not.
No. No, you could jump, but it would be exactly the same on a moving train as it would a still one, right? Okay, so there's nothing, you drop something, it's gonna go straight down, whether you're moving or sitting still. That was stuff we talked about before, right? But now, let's take it a step further. Let's say you're riding on this thing, and suddenly, this train turns left. What's gonna happen to you? You're gonna go to the right. You're gonna feel like you go to the right, correct? Okay, the train turns left, you go right. All right, you say, hey, now I know I must be moving. If I was sitting still, that wouldn't have happened, correct? All right, however, what if you were just sitting still and all they did was lift up the left side of the car? Wouldn't you still just fall to the right? Okay, what about the train car turning to the right? You'd go left. Is there any difference between that and then just somebody just, while you're sitting still, lifting up the left side of the train car? And you'd fall left. Is there anything you could do to tell the difference between those two events?
How fast you moved?
How fast did they turn it up? How steep did they make you, right? Yeah?
Deceleration?
Okay, so let's say you're going along and they hit the brakes and you go flying forward, right? Is that really any different than someone just lifting up the back of the train?
Wouldn't it be your orientation?
You can't see. What are you orienting with, right? The windows are closed. Can't see out of them. Yeah.
If they were tilting, wouldn't there be some sort of vertical component to the tilt as well? Like if you were just turning and you were braking, you'd kind of be more of a lateral.
Okay, so if you're braking, you still have gravity pulling you down, and now you're also moving forward, so there is kind of an angled motion to that.
But you have
And if they turn you up like this, then it's gravity pulling you straight down, which is still angled to the floor.
yeah, but isn't there more drastic like pushing down?
It depends how much they lift you up or brake, right? But for any braking we come up with, we could come up with a a gravitational situation where we do that, and you can't tell the difference.
So is the answer no?
Well, maybe. I have an example here in just a second. Yeah.
But if you could definitely go up,
Why would, well, you wouldn't know you were going up though, would you?
like you leave your seat though.
You'd leave your seat if they stopped too. You'd go flying forward, right?
Yeah, but
If you were sitting, we were standing up, but yeah.
But if they were like braking super hard, wouldn't you like slowly come to a stop? But if they lifted you up, like it would be immediate.
What if they just slowly lifted you up?
I'm going with no.
And if they suddenly started speeding up and you'd lean back, then couldn't we replace that just with a lifting of the front of the car? All right, let's think of something here. This one, this little example right here for telling the difference, let's just go to it. You ready? Let's say we have a box, and this box is filled with air. And we go inside there and we put a little balloon right in the center of the box, and this box is just sitting on the ground. And we let go of this, it's a helium balloon, by the way, that probably would help, huh? And we let go of this helium balloon. What's it gonna do? It's gonna go up, right? That helium balloon is gonna go up towards the top of the box. It's gonna do this because with this box sitting here on Earth, the air at the bottom of the box is more dense than the air at the top of the box because gravity is pulling down on it, okay? And so what the balloon tries to do is it creates an imbalance in pressures on it where there's more air down here around it than there is up here, and it therefore squishes that balloon and pushes it upward. So it's a difference in pressures between these two. Causes the balloon to go up. Now let's take this same box, and instead, hopefully that's done. It still seems laggy on my side, sorry. All right, and instead let's take this to outer space. We're not near a planet or anything, we're out in outer space, there's no real gravity around. But we have the same exact box, same air in it, same balloon, and we put the balloon right in the middle of the box and we let it go. What's it going to do? Nothing. It's not going to go anywhere. It has no preferred direction to go now. There's just as much air above it, to the sides of it, below it. The pressures are the same in all directions, and it doesn't go anywhere. It stays right there. Okay? So let's go back to our train. Okay? And let's this time take a balloon with us, a helium balloon. And you're going to hold this helium balloon, right? You're totally enclosed. You can't see. You know, you're going down this track that you can't even feel. There's no bumps or anything like that. You're holding this balloon, and suddenly the train turns left. And when the train turns left, everything in the train goes to the right. You lean to the right. Your keys go to the right. Stuff on the floor slides to the right. And the balloon does what? It goes left. It goes left. What if you were sitting still and we lifted up the right-hand side of, the right-hand side of the car? Right? Did I say that one correct? Or did I flip-flop that? I'm sorry. Whatever it is. You lift up the right-hand side of the car, everything's going to go left, right? Everything's going to go the opposite side. That's like turning to the right, is to lift that side up, right? Everything goes down, except what? The balloon goes the other way, up. So even with this example, which I know I usually start this example as here's the actual example that shows how you can tell, you can't even tell. Because as you turn, all of the air is gonna, you lean to the left, everything leans to the left, so does all the air. It compresses on one side. And so therefore you get a pressure differential from left to right, and the balloon goes the opposite direction that everything else does, just like it would in a gravitational field. Okay? And so this idea has now been around for over 100 years, and this is what is called our equivalence principle. And it's the idea that there is absolutely no way to tell the difference between a gravitational field and accelerations. No way to tell the difference. So we could take this box right here, and we could ask the question like, well, how would we know if this box was floating in outer space or sitting here on the surface of Earth? Well, you put the balloon in the middle and let it go, correct? If it goes up, you know you're in outer space. Or I'm sorry, if it goes up, you know you're on Earth. If it stays in the middle, you know you're in outer space. But what if we attached a rocket to this? And we put a rocket on the bottom of this, right? That's the fire coming out of the rocket, okay? Yes, my next talk will be about, art, so we'll get that going. Okay? And we had this accelerate our box upward at 9.8 meters per second squared. What would the balloon do then? Would it stay in the middle anymore? Because as we're accelerating up, what's going to happen to the air at the bottom of the box? The air is going to squish down to the bottom. We're going to get a pressure differential. The balloon's going to go up. It's going to go the opposite direction of our acceleration, just like it did on the train. So then this becomes the question. You're in a box, you can't see out. There's no windows or anything. Is there anything you could do to tell whether or not you were sitting on the surface of this planet or whether or not you were in outer space and they were accelerating you at 9.8 meters per second squared, which is what the acceleration due to gravity is here on the surface of Earth? Is there anything you could do? If you drop something, you're standing in that box, and you're on Earth, you drop something, it'll fall down to the ground at 9.8 meters per second squared, right? If you're in outer space and it's accelerating, you let go of the object, then it's basically like it stops accelerating and the floor rushes up and hits it at 9.8 meters per second squared, and you go with it. Can you tell the difference between those two things? And the answer to this so far has been no. Absolutely not. We cannot tell a difference between these. We'll come up with a situation here in a little bit that kind of does, but yeah.
So the acceleration upward is 9.81, and on Earth the gravity's down 9.81. So what is the object doing? Is it?
That's the next part.
Oh, okay.
Free fall. So in free fall, normally that's just you let go of something and you let it fall. And it accelerates downward. And that's how we learned it in, that's how you learn it in your first physics class. You drop something, it accelerates downward. In Einstein's picture here, that is not the case anymore. Okay? Free fall is actually the situation where you have no acceleration. Now I'm trying to remember how many L's are in acceleration. 2 L's, thanks. Thanks, Mom.
Mm-mm.
It's just 1. Thanks, Mom. That's an R. Acceleration. All right? Free fall is when you have no acceleration. That means if you jump out of an airplane to do like skydiving or something, that feeling you get, or when you go on a roller coaster, you start to fall, you get that feeling in your stomach. That's not the feeling of falling. It's not the feeling of accelerating. It's the feeling of not accelerating. Right now, where you are just extremely used to it. You feel the feeling of being accelerated upward at 9.8 meters per second squared. And it's only when that is removed that you feel that in your stomach. Basically, in free fall, you are weightless. You cannot tell the difference between free fall and being weightless. You cannot tell the difference between gravity and acceleration. So therefore, if you can do absolutely nothing to tell the difference between them, then they're the same thing. And in fact, Einstein said, if you want to understand gravity, understand acceleration. So if we look at this picture of it, we are not standing here on the ground being pulled down to it, but rather it is pushing up on us and accelerating us upward. Almost like it's just constantly, everything's constantly expanding outward. And we just happen to expand exactly with it, and therefore we don't notice it. Okay? There's nothing we can do there. Free fall means no acceleration. Okay? That's why you put astronauts in orbit and they're up like 100 miles up, and their force of gravity there, if you calculate it, is still like 90-something% of what it is here on the surface. But yet they're all weightless because they're all in free fall. They're in constant free fall. They feel weightless. They don't feel the gravity because they're in the middle of that free fall. This one I think is a lot more difficult to kind of take in and swallow than our previous we can't tell who's moving and not moving. It's even worse now. Because now we can't tell the difference between this acceleration and gravity. We can't tell if we're on a planet or not or anything like that. So that's our equivalence principle right there. All right? You cannot tell the difference between gravity and acceleration. And in fact, if you've taken any class in physics, we had 2 different types of mass. We had inertial mass and we had gravitational mass. One of them was the amount of mass that dictated how much gravity pulled on something. And the other was the inertial mass, which was in that F equals ma, that told us how difficult it was to accelerate something. And we pretended they were the same. And in fact, prior to Einstein, it was a long time known that they were somehow related. They seemed to be the same, but no one understood why. They had some sort of link between them. And it was Einstein's equivalence principle when he came along with this that said they are not only related, they are the exact same thing, and they have to be. Gravitational mass and inertial mass have to be the same thing. All right? They cannot be different masses. And so they are. So now let's think of a really crazy situation. And we're going to talk about the example I ever heard of this. It's Million Mile Man. So let's pretend that we have a planet over here. Okay? And we put one object way out here in space, and it's going to feel a pull of gravity straight down towards the center of the planet. Okay? But we also have some objects over here, and over here, let's say. And they get pulled straight down toward the center of the planet as well. What's going to happen to these objects as they fall? As they get closer and closer to the surface of Earth, what else is going to happen to them? They accelerate, they go faster and faster, and when they get to the ground, By the time they get there, look at this part. What can you tell me about those separations?
They get closer.
Yeah, they get closer together. They get closer together. All right? So there's the difference. If we were on a spaceship and we were in this huge thing and we were accelerating upward, and we dropped those two things, they'd all stay the same distance away from each other, right? Like if it was here's a spaceship and this one was falling and this one was falling, or the ground was, or I should say, this one's accelerating upward. But these would all stay the same distance apart. But here with the planet, because the planet is round like this, we don't have that. We have them getting closer together. Okay? What about Million Mile Man? Let's pretend we have someone standing here who's 1,000,000 miles tall, real big. Okay? Right? This makes it extremely obvious. But his feet are closer to the planet than the top of his head. And in fact, that's true for us here right now as well. Your feet are closer to the planet than the top of your head. And therefore, his feet have a stronger gravitational pull on them than the top of his head does. So he's got a bigger gravitational pull on his feet than at the top of his head. What about over here? Million Mile Man, real big. Is there a difference in the acceleration towards the ground for the top of his head and his feet there? No. Not with the ground accelerating. It's the same acceleration the whole way up. Okay? There's no difference there. So it sure seems like we're suddenly in a position where we can tell the difference between gravity and acceleration, correct? If we go to a large enough scale. Because if we go to a large enough scale, we get things that start to squish together, and we also get things that get stretched because his feet are being pulled more than the top of his head. That's how we would know we were in a gravitational field there, versus just the pure acceleration one, where it'd be the same for everything, it'd be uniform. Okay, that's how we can tell the difference. All right, and those are called tidal forces, by the way. That's what makes us have tides and stuff on this planet. It squishes down and gives us tides on both sides of the planet. But those tidal forces are where you can really recognize the difference between gravity and acceleration. Does that mean the equivalence principle doesn't hold anymore? I would argue absolutely not. Because you have to remember something here. The only forces acting when we talk about the equivalence principle is gravity. If we're looking at this, that's not the only forces we have going on, right? In Million Mile Man, is there only gravity working on him right there? No. He's got forces that attract all the particles that make him up, hold him together, right? He is not, as far as physics is concerned, just one thing. He is a collection of things, and those tidal forces he is feeling is those collections of things pulling each other away from their normal, just straight, absolutely indistinguishable from gravity type acceleration. So the only way we can tell the difference between the two is to have other interactions be introduced, to put multiple objects out there and then have them interfere with each other. If it is just a single object, though, you can't do it. You can't tell the difference. And we live in such a scale here, for short periods of time, on small scales, where we can ignore that even the stuff we're doing these experiments with is made up of multiple particles and multiple individual things. And therefore, we can still use this equivalence principle as a very close approximation, even just on our scale. All right, I believe when Einstein works out gravity and stuff for this, it stays accurate to like 10 to the 14th decimal places. It's crazy accurate. Really, really accurate, just from this idea. Okay? And there was no experiment that told him this. He just kind of thought of it and came up with this idea and was able to, just purely off of the speed of light being constant and this idea here, to come up with all of this and figure out gravity and black holes and all this stuff, which I always found to be absolutely amazing. So tidal forces, that's stuff we can look out for, but it only really occurs when you have multiple objects interacting with each other. So we'll stay away from that. Now let's go back to our spaceship. if you're on a spaceship, okay, and let's put you in the spaceship, and say the spaceship's just floating there, and you're standing in here, and there's a little window right here, and someone shoots a little beam of light in through the window, you would see that beam of light go straight across and hit right across from the window. Okay? But if we instead added an acceleration here, some more of my very good fire, all right, and it started accelerating upward, you'd suddenly stick to the floor like you're in, you have gravity now suddenly, and this beam of light, as it starts to come through the window, it comes through at this point right here. Let me see if I can zoom in. It comes through at this point. I need a different color. It comes through at this point right here. But then as it moves to the right, the ship moves up a little bit. So the next point, it's over here. And then the ship is going even faster. So the next time the light moves a little bit to the right, it's moved even more. And more, and more. And the path you end up getting is a curved path where light suddenly curves down. And so this idea here that he got from this thought experiment was that gravity must affect light. And there was no experiment that said this was true. No one had ever witnessed this or seen this. It was just something he came up with. And it wasn't even until years later after he had done this that it was actually found that this was correct. This was correct. This acceleration bends light, and if acceleration does it, then so does gravity. And it turned out to be true. In fact, there was the example, it's called gravitational lensing, where we were here on Earth, let's say, and we had the sun way over here, and we had to wait for an eclipse to occur. But it basically blocked out the sun. Now, there were some stars that were supposed to be really, really close to the edge of the sun, like the star was over here, right? And it was supposed to be really, really close. And what happens, the idea is that any light that would have come toward us, like that, is actually going to get affected by gravity and get bent away, and we're not going to see it. And any light that was coming over this way that we wouldn't have seen gets bent over and comes to us. And so that when we would look out at this star that should be near the edge of our sun, it should appear to be in a different location, in the wrong location. And it was actually years after he released this that an eclipse finally occurred, and they looked up their telescopes, and they were off by the amount he predicted. They were out of position, just like he had predicted, simply from this idea that you can't tell the difference between gravity and acceleration. And it worked. It worked very well. Okay, so we have bending light, and that tells us that gravity bends light. Okay, and we get positions of stars out of place. There's lots of interesting pictures about it. We can see like multiple versions of a star because it got lensed around like a galaxy and things like that. But this kind of thing, it does happen, and it's going to be kind of a big deal for us. Now, you've often heard that the shortest distance between 2 points is a what? Straight line, right? Now, light is going to always travel the shortest distance if you send it between 2 points. It's the fastest that anything can go. It's always going to do that. But what does that tell you if light is now traveling in bent, curved paths between 2 points?
It's using acceleration.
That's not the way Einstein looked at it.
Okay.
It tells you your straight lines are curved. All right? It tells you your straight lines are curved, that we no longer have flat space. Instead, what we have is called a curved space-time. And this is that idea, which I'm sure many of you have seen before, where they say, this is Einstein's theory of gravity, and they have this big rubber sheet stretched out, and they put a heavy ball in the middle of it, and it sinks down and curves the sheet, and then anything they try to throw around it curves around the bends and everything like that. They were saying that because they're talking about Einstein saying that this is a curvature of space-time. Our straight lines get turned curved. Okay? They get turned and they're curved. And those straight lines, we don't even call them straight lines anymore, we call them geodesics. This is a straight line in a curved space. If you want to come up with a geodesic and understand what it really is, imagine you had to drive a golf cart on some hilly, mountainy, rocky place, okay? But you couldn't turn the steering wheels at all. They were locked in and they just went straight, no turning. The path that that golf cart would travel would be a geodesic. It's the straightest possible path that you can do, okay? And you figure this out with something called, parallel transport, which I'm gonna go ahead and skip now because I just noticed the time. So, but basically, you just try to move something as straight as you possibly can. That's a shame, it's so super interesting. Should I talk about it or no? Sure, why not, right? So what you want to do is to know if a space you have is curved or not. I really thought it'd been like 10 minutes. If you want to know if a space is curved or not, in fact, I thought I was going too fast, you parallel transport. And so the idea is, if you take something that's like a spherical surface, and imagine this is a sphere, and you start with a little arrow that's right there on it. And then what you do is just move it a tiny little bit, and then you reline it up with the surface. So if it's going across the curve, we're here, we move it a little bit, and then we turn it so it's tangent to the curve again. And then you move it a little bit and tangent, and so you get it as parallel as you possibly can to the previous one. So you move to your new little point that's just infinitesimally far away, and then you line your vector up as close to what it was originally as you possibly can. All right, that's a parallel transport. If you parallel transport around doing this, you will end up getting to the top, and then you parallel transport around over here on the side. You transport this way, this way, this way, and then you come back around this way. These are all my parallel transports, right? So I went parallel transported up around the sphere, then I moved down, and then I came back. And what you find when you get back to the original starting point is that your vector is no longer pointed in the same direction that it was when you started. If that is the case, you're in a curved space. So you would go up, parallel transport, parallel transport, parallel transport back to your starting space. I started pointed this way, I ended pointed this way, even though I'm back at my original place. Therefore, I'm in a curved space. If you do this on a flat sheet, right? And I have a vector here, right? Flat sheet, or even like this. I parallel transport up, parallel transport over, parallel transport down, parallel transport back to the start. It's parallel to how it started. That is a flat space. Think about something like a cylinder. Okay? Let's look at a cylinder. And we're looking at the surface around the edges of the cylinder. Is this a flat space or a curved space? Did you do parallel transport before you answered that?
Yes.
This is a flat space. All right? You can make, a cone. This is flat, right? If I just make it into a cylinder like that, still the surface is still the same surface. And if you parallel transport around it, right? You go up, you go over, you stay as parallel as you can everywhere, you're right back, it's still in the same direction. It's not the same as it would be on a sphere. Same thing for a cone. A cone, if you have a cone, like that, maybe I should have brought bigger piece of paper, but if you have a cone, it's actually flat space everywhere except at the end. At the end it's not flat, but it's flat all over here if you do your parallel transporting. And so, that parallel transport is how you actually tell whether or not you're looking at a flat space-time or a curved one. You parallel transport through it, okay? And whenever something is going through that space, it's gonna follow those geodesics, those straight lines. Now, oh, I forgot no, I didn't, that's okay. So, you have to be careful with this because if we're talking about the ground and we're talking about that golf cart, no matter how fast you drive the golf cart, if you can't turn the wheels, you're gonna follow that same path, assuming you don't jump and ramp off of anything. But going really slow versus going faster is not gonna make a difference. this almost wants you to think that everything is going to follow the same path in a gravitational field, and that is not correct. All right, if we threw you out from the same place as light would keep going straight up and probably escape the planet, and you'd fall down into it. So a geodesic isn't just a curve in space, it's a curve in space-time. And so your speed actually affects the path of your geodesic. Okay, the faster you are going, the straighter your geodesic will be. If you're just moving slow, it'll curve you down more, and gravity will have that bigger impact on you. So don't think of it as just because remember, this isn't just a physical space, this is a space-time, and they are intertwined. And so that's what those geodesics are for. They tell us our paths, okay? And light does the straightest path, which is curved. So you have no straight lines, you only have curves. Now it's time for the equation. And this is basically just to show you, people talk about how wonderful and beautiful this equation is. And so I'm going to write it for you. And it's this. And I have to look because there's no way I'm going to remember this one. All right, so R minus 1/2 R G nu. And then this equals 8 pi G over C to the 4th T mu nu. And this is Einstein's field equation. This is what dictates gravity. Now I had also gone ahead, and I will, for time's sake, I'd also written out what each of these terms looks like. You start with what is called the Riemann curvature tensor that contains two partial derivatives of, think of this curvature tensor, that R. You start off with this R that is a 4 by 4 by 4 by 4 matrix, each filled with what are called these Christoffel symbols that are all 3 by 3 by or 4 by 4 by 4 matrices at each location, and they have derivatives of them. All right, and that's the Riemann curvature tensor. You then contract that down, and I know you can't really see this, but you contract it down to just R mu nu right there, which makes it a 4 by 4 tensor matrix type thing, right? You do that, and you have that Riemann curvature tensor that goes in there right there, that has all those other crazy terms in it, all right? And then each of those terms that you're taking derivatives of, right, are these little Christoffel symbols. And again, I know you can't really see them, but you can see all the writing I did out here, okay? You have a whole bunch of other little things of derivatives of other matrices. So this is like matrices inside of matrices inside of matrices to come up with this thing. And then you can condense it down even more. You can contract over these two and get what is called the Ricci scalar and the Ricci tensor right there. And all of that simply describes the shape of space. All right, and in fact, this part that you have right here, that little g, that's called the metric of the space. So that tells you how curved your space is. So everything, and even these R, even this R that's right here, is made up entirely of different derivatives of that matrix, all put together in different positions to make the Christoffel symbols that then are put together to make the Ricci tensor. And it's crazy complicated, even though it looks a little not too complicated right there, but it is crazy complicated. And you don't want to work this out by hand. That's why almost all the problems we do in this are worked out by computers. They're very good at computing for us. All right, this is crazy difficult. But everything that's on this left-hand side, the point of me saying this, everything on this left-hand side is all about space. That's all about the shape of the space. That's it. Over on this other side, we have some constants right there. And then we have this here that's called the energy momentum tensor. So we talked about before how if I put, we're not going to agree on the motion of everything. So we're not going to agree on the kinetic energy of everything. And we're not going to agree on the momentum of everything. but we will agree on these tensors. So if you put together energy and momentum together into this tensor, we all agree on this tensor. So this is all the mass energy over here. So if you think about what this is telling you, on the left-hand side, this is space telling the right-hand side, which is all the mass energy, what it should do. And if you think of it the other way, the right-hand side is all of the mass telling the left-hand side how it should be shaped. So mass tells space how to be shaped, and then the shape of the space tells the mass how it should move. And the energies of how it should move. All right, and that's what you get from this. One side completely space, one side completely mass energy. And in fact, you can solve this. In fact, anything you find that is a solution to this, that makes these two sides equal each other, what you can come up with, you try to come up with a metric, that little part right here, and if it works and it solves this, then you say this is a possible thing. Some examples of things that solve this, there are waves that solve it. There are wave equations that solve this, which is where we got the idea for gravitational waves, and they've been detected. Black holes were a solution to this. Einstein-Rosen bridge, wormholes, these things, they're all solutions to this. If it solves this, the idea is then it's possible. If you cannot solve it, if you cannot come up with a metric that will solve this out, then it's not a possible thing to do. All right, and that's the major thing that is worked on. Okay, last couple little things. Or maybe I should save these for next time. What do you think? It's 5:08. Save it for next time?
Yep.
Yeah?
You can use
Oh
that.
no, we didn't even get to explaining mass. Okay, I have to do this real quick.
Okay.
Okay, we have to. So, with gravitational shifts, we get things that change. Our clocks change. So imagine if you try to send, let's see here, if you try to send light up from the ground, right? So you start off with this light you're sending up for the ground. It's going to actually lengthen as it goes along. All right? Or if we think of it the other way, let's put it this way. Let's say that's the ground, and let's say we send in this long wavelength, and as it gets closer and closer to the ground, because remember, we're thinking of the ground as accelerating upward towards it, then it's going to get compressed in the wave. And it's going to get like Doppler shifted. Okay? And then the same thing going the other way. You send the light wave up, it's going to stretch out. And so if this happens in an accelerating circumstance, it happens in gravity. This was another thing that was actually confirmed. There was a scientist who did this. He went to a really, really tall skyscraper, and he actually shined a light all the way to the top and measured that there was a difference in the frequency of the light from the top to the bottom of that big tall building. So that actually works. This you can think of as time dilation. So imagine you're down here on the ground, and every second that goes by, you send out a new wave, right? But as it goes up, it stretches out. And so someone sitting way up in outer space waiting for your signals to come, they're not going to get a wave every second. They're going to get it at intervals that are longer than a second. Which means if you're in this acceleration thing and you're sending out time, right, you're going to have a time dilation curve. Your clocks are going to be slower when you're down in that gravity because it also works with this acceleration. So the bigger a gravitational field you're in, you get slower time. Okay? So we also have time dilation with this, not just with special relativity, but gravity also slows down and affects time. Now I want to talk about this last little bit, promise. Okay? So we had our light clocks before, and we used them to come up with time dilation and relativity. But let's move them a little differently now. Instead of just having them go to constant speed, let's accelerate them. So let's start here with, let's say we have a box. And in this is a box, it's made out of some magic material that has no mass. And we put it on a scale, right? And we see that it has no mass. But the inside of this box is totally covered with mirrors. And so we throw some photons in there, some little bits of light, and they start bouncing around in there. All right, will that scale be any different when we throw the light in there? Light is massless, the box is massless. Will the reading on the scale be any different? Yes. Yes, it will. It will suddenly start to show that it has mass, even though we haven't introduced any mass to it. We've only introduced some light to it that has no mass. So let's think about this light clock. Let's say we have this light clock and we're going to bounce the light there and bounce it back, but we're going to also accelerate this forward in this direction. Okay? We're accelerating that direction. So when we first send the light out and it heads towards this side over here, that side is moving away from it. Anybody ever try to play a sport where you had to catch a ball or play soccer and that ball's coming in? Do you just stick your foot there and let it hit your foot and bounce way off? Some of you do, but should you do that? No, you're supposed to bring your foot down with it, right? Slow it down slowly, right? You ever seen the Mighty Ducks and they do that with the eggs on the ice? And they have to accept it nicely. If they just stop it, it just splats. So you accept it and you slow it down nicely. So you move with it, right? So it's not as big of an impact. So what happens here is the light, as it shines towards the side in the direction that we're accelerating, it's going to hit that wall and it's going to give a little bit of a little momentum hit to it, a little push to it, right? But the wall is moving with it, so it's not as strong of a hit as it normally would have been, okay? If we're sitting still, then it's just a normal hit. And then it goes back to the other side and it's just a normal hit, and the two hits just cancel each other out. If we're moving this way or accelerating this way, then the hit isn't very strong. But then when it goes back to the left to hit this side over here, that side is rushing toward it. So when it hits that side, what's it going to do? It's going to hit it harder, isn't it? Okay? So if we're sitting still with this light clock, it's like nothing's going on. It's hitting both of them the same strength, and it's canceling out. If we accelerate it to the right, we end up having that light hit on that left mirror harder than on the one in the direction we're trying to accelerate it, which means we have a resistance to trying to accelerate it. If we do this in our light box, anytime you try to accelerate it in any direction, that light's going to slam into that side that you're accelerating toward it more than the side that's accelerating away from it, and we're going to get an overall pressure that resists the acceleration of this object, right? What is mass? I really hope my physics students can answer this one. How do we measure mass? Or what is it a measure of? That's right, I'm going to pretend you answered. It's a measurement of inertia. It is, mass tells you how much a certain object resists being accelerated. Just like this does here. So we've taken a massless thing, a photon, a light, and we're somehow getting a resistance to motion out of it, a resistance to acceleration, which is just what mass does. And I'm going to tell you right now, this is mass. This is exactly what causes mass. Okay? So let's change this down. Let's think of an atom. Here's our nucleus, here's our little electron in orbit around it. How does the electron stay in orbit around it? Well, they actually exchange photons. They send little force-carrying photons back and forth, just like our light clock. If we try to accelerate this, say we try to accelerate in this direction, then the photons are going to slam into one side harder than they do the other, and there's going to be a little resistance to that motion. It's going to resist us trying to move it, just like in the light clock. And this happens down in the atoms. If you take the quarks that make up the protons, they're exchanging little particles, like little light clocks. And if you try to accelerate them, you get that imbalance of pressures, and you get a resistance to that acceleration. In fact, you can account for just about all of the mass that we see just by these effects. Just by this bounded effect of these things, where you have them all hooked together like that with these little light clocks. And it resists acceleration, which is just what mass does. You can account for all mass. The only thing you can't account for is a tiny little bit, is that if we have an electron by itself out in the middle of space, it still seems to have mass, even if it's not bound to something. And that's where the Higgs boson comes in, to explain that extra little bit of mass. But it's all this binding energy. That's what that is. Remember learning about binding energy in your chemistry classes? It's all because of these little exchanges between them. All right? So it turns out, that I guess should have gone down here. I was talking about atoms, but yeah, that's all mass is. It's a relativistic effect. If you feel mass, then you have a resistance to acceleration because of this. If you are a massless particle, it means you're not feeling this effect. You are the cause of the effect, like the photons are, and they can travel at the speed of light. By the way, speed of light, not really about the speed of light. It's actually about the speed of information. And I'm going to leave you with that thought because I'm going to get into that next time. Okay? Any questions? Have no idea what to ask? Wake up? Nobody can even think of anything to even ask her. I know my father proclaimed he was going to come up with questions to ask me and made me look bad, but. No? Okay. If you think of anything or you want to see more of these little equations that I so nicely wrote out and looked all up in my old general relativity notes and stuff.
You could take a picture of them really quick.
Of what?
Just the notes, like
Oh.
just pull up the camera on your iPad.
Yeah. I will later.
Okay.
But if you ever want to see them, I hunted down my old relativity notebook and grabbed these out and searched through it for y'all, but didn't get to share them. So. Huh? Thank you, honey. All right. Thanks, everybody. Next time, black holes.